slowing aging down might give us a little bit of extra life. Reversing aging, even relatively uncomprehensively, will give us essentially indefinite life.
Hope you enjoyed the episode, brought to you by our sponsor, Thrive. Get 50% off your at-home gut health test when you go to trythrive.com/impact theory. Enjoy the episode. Hey everybody, welcome to another episode of Health Theory. I am joined by somebody who is really an incredible thinker when it comes to anti-aging, gerontology, has a very unique approach to that. His name is Aubrey de Grey, and he is the Chief Science Officer at the SENS Research Foundation. Aubrey, welcome to the show.
Well, thanks for having me. Great to be here.
I'm really excited. You have keen insights into one of the areas that I find most interesting in the world, which is, can we live forever? So I've been telling people for years that I want to live forever, and they look at me like I'm crazy. And I never understood that. And researching you, I realized this is something that you have come up against a lot. And you call it the pro-aging trance. So I'd love to hear, one, do you actually want to live forever?
Well, to be honest, I don't really think very much. In fact, I don't really think at all about how long I want to live. I think it's really a pretty strange thing to have an opinion about, to be honest, because really, it makes no sense to have any opinion about something that you can change your mind about in the meantime. You know, I compare it to having an opinion about what time you would like to go to the toilet next Sunday. You know, you may have an opinion about what time
How can that be possible? It's so, like, literally the difference between existing and not existing. You don't think that people are going to have a pretty strong sense of whether they prefer one or the other?
Again, you know, you're mixing up what people want and what people expect. So, of course, one has an opinion about what time one expects to go to the toilet next Sunday because of habit, right? So, but having an opinion about what time you want to go makes no sense because you're going to have better information on the topic nearer the time that you're going to be able to act upon, right? So it's exactly the same in my view for how long you want to live. That depends on your quality of life at the time, which in turn depends on all manner of things that we don't know about. You know, like how good medicine's going to be, you know, whether there's going to be a nuclear war, you know, all manner of stuff. I have absolutely no idea how long I want to live, but I do know that I want to have the choice. I want to make sure that my choice about how long to live and of course how high quality that life will be is not progressively taken away from me by aging. So that's all really. It's just an investment in having choice.
That's really interesting. And so now as you're approaching the research and looking at how we extend sort of high functioning life, and I think that's probably important to define. So let's get right into the idea that you have that really differentiated you from everybody, certainly, you know, 10 years ago when nobody was echoing your sentiment. What is different about the approach that you have with SENS versus sort of the standard approach before you presented that?
So 10 years ago, I'd more or less won the argument. And, you know, that became really apparent 8 years ago, in 2013, when a group of my colleagues published a paper that's very famous now. It's called The Hallmarks of Aging. And it's pretty much exactly a restatement of what I had published more than a decade earlier. And it is tantamount to holy scripture in the field. It is the paper that it's been cited far more often than any other paper in the whole of the biology of aging in the past decade. And it simply describes this kind of divide and conquer, damage repair approach to aging, same as I did. So, yeah, by 10 years ago, it was over. I had won the argument. So when I came along 20 years ago and said, listen, we could do this damage repair thing, we could actually turn back the aging clock, and it should be easier to do that than to slow the clock down, which is what people had been trying to do before. First of all, nobody understood anything I was saying. I was bringing in a lot of biology from areas that had not historically been considered relevant to the biology of aging. And that, of course, meant that the people who were studying the biology of aging didn't know about them. So there was a lot of, getting up to speed involved in this. But yeah, I mean, just the general concept, even in the abstract, that reversing aging could be easier than retarding aging just sounds wrong. It sounds like reversing aging is a bigger thing, and therefore it's got to be harder. And so, yeah, the idea, all I had to get across really was that when we're slowing aging down, we're interfering with the processes that drive aging. Whereas when we are reversing aging, we aren't. What we're doing instead is we're repairing the consequences of those processes, the damage that's already been laid down. That's completely different from retracing and, kind of running the processes in reverse. It's not like that at all. If it were, then yes, absolutely, reversing aging would be far harder than retarding aging, but it isn't.
It's really interesting. And so, one, do you think that the early pushback on that had to do with just they weren't aware of some of the biology that you were bringing into the debate? Or was it something where they just couldn't accept that it would one day be possible to rejuvenate old tissues?
Well, really, there were three parts. Both of those parts were somewhat true, but they understood that I was basing my work on real biology. They just, it takes a while to catch up. Biology is an enormous subject, and nobody knows more than a tiny proportion of it. So really, it was just a case of the conclusions sound really surprising, therefore he's probably wrong. And I was, I benefited a lot from the fact that before I started talking about all of this in about the year 2000, I had maybe 5 years in the field in which I had been having good ideas, other good ideas that were relatively uncontroversial and were well received. So everybody already knew that I was smart and knowledgeable and all that. So they knew not to dismiss me too easily. But still, it was tough. But the third thing, which you haven't mentioned, was the really big one. The problem was that right from the beginning, I was perhaps a little bit too fearless in what I said about the consequences of all of this, in terms of how long people might be expected to live. Because that, of course, comes down to this thing I've mentioned, which I guess you're going to ask me about coming up, called longevity escape velocity, that leads me to the conclusion that whereas slowing aging down might give us a little bit of extra life, reversing aging, even relatively uncomprehensively, will give us essentially indefinite life. So, that's politically incendiary. It sounds like I am not a scientist. And scientists really do not want to share a platform with people who sound like they are not scientists, however smart they know that those people are.
Now, were you getting out over your skis from the biology perspective at that time? I mean, obviously people have come around now, so something we've discovered makes this far more plausible. Were you intuiting that this could become true? Or were you sort of rationalizing from first principles that there's nothing unrepairable happening at the tissue level? Like, how did you come to that conclusion?
Yes, I was saying, well, look, the body's a machine. It's made of atoms and molecules and stuff, right? Its function is determined by its structure. Therefore, restoring the structure will restore the function. Therefore, the only real question is, are there aspects of the structure that are inherently, even in principle, impossible to restore to how they were in young adulthood? And it seemed to me that, no, there obviously are not. And nobody came along and said, yes, there are. The only real difference at the beginning was in terms of the degree of difficulty of this thing. And of course, even now, most people would be somewhat more pessimistic than me in terms of that, and therefore in terms of the time frames for developing this or that damage repair technology for this or that type of molecular or cellular damage. But we're within each other's range, it's not that we think we're crazy about this. And even right back at the beginning, when I was first talking about all of this, as I was bringing together a lot of different ideas from different areas of biology, because of course the damage repair approach is inherently a divide and conquer one. The people who
what
were
do you mean by
specialists.
divide and conquer?
Oh, simply that there are lots of different types of damage. We've got to fix them all, and each of them is going to be fixed by a different technology. And therefore, you've got to apply the same technology, a lot of different things to the same people at the same time in order to get the result. That's all I mean. Right. So, yes. So when I was talking to the specialists
Understood.
in any given particular area, like, for example, mitochondrial mutations, I would generally not see very much pushback from those people in regard to their area. I might be a little bit more optimistic than them, but I would be basically talking sense, and they would understand that I knew where I was going with this, and, they wish me luck. But when you ask these people about each other's area, about which they knew very little, they would immediately throw out their hand and say, oh, this is complete science fiction, there's no way this can work. So this was the kind of, consequence of the balkanization, the siloing of expertise in biology that has happened increasingly over the years. And it took a while to break that down.
That's actually a really interesting insight, that the more somebody knew about the area, the more plausible your take on things seemed. But the less they knew, the more then they're sort of defaulting to a base assumption that they have about longevity itself. And now, is this where you see people spilling into just sort of a dogmatic approach about humans are never going to live forever? I'm not willing to let myself become optimistic about that. People for thousands of years have been saying that they've cured it and people are going to live forever. Is that what you're up against?
Yes. But it's kind of even more than that. Because on top of the fact that this is aging, and everyone's been saying this since the beginning of civilization, and therefore, everyone's been wrong, therefore I'm likely to be wrong as well. On top of that, there is the general fact that within science overall, experts are very reluctant to risk overpromising and under-delivering. They really, really want to just, whenever they have the misfortune to be talking to the general public, they want to say, we don't know. In most walks of life, saying you don't know is the opposite of what you want to do. You want to pretend you do know stuff that you don't know. In science, it's the other way around. You pretend that you don't know stuff that you actually do know.
That's actually fascinating. And there is something to that sort of level of humility that I like, but it can obviously distort and itself become pathological. So I think now it's a good time, because I want to frame, we're going to get into the weeds of like what the 7 types of damage are and what the sort of antagonistic thing that we apply to that to repair will be. But now I think we do need to get into what the escape velocity is here and what you think will ultimately happen. I don't want to put words in your mouth, but when I hear you speak, maybe I hear what I want to hear, but I hear sort of the ultimate hope. But before I put words in your mouth, when you talk about escape velocity, what do you mean?
Right, yeah. Okay, so let me give a nice, bit of background to it. So, at the end of the day, because, as I mentioned earlier, the human body is a machine, and therefore its function is determined by its structure, we can therefore say that the health of the body, and therefore the likelihood that the body will cease to function at all, in other words, that we will die anytime soon, is determined by the amount of damage that the body is carrying around. And this damage, the damage we're talking about anyway, is a result of the body's normal operation. In other words, it is self-inflicted. We are inflicting this damage upon ourselves throughout life, even starting before we're born, because this is simply consequences of things that the body needs to do. And it's really intrinsic consequences. There's no way that we can have the body actually, keep us alive without the body also creating and inflicting this damage upon itself. In that sense, aging of the human body or of any other living organism is no different than aging of a simple man-made machine, like a car or an airplane or whatever, that accumulates rust as a result of, the rain. What this means is that we could, in principle, improve the likelihood of living a bit longer just by repairing some of the damage. But it's better than that. the key thing that we have to take into account, and again, this is just as true for living machines like you and me as it is for inanimate machines like cars, is that machines are set up to tolerate a certain amount of damage without any really appreciable decline in function. So this is why the health problems of late life are problems of late life, and we do not see them at all until after middle age. There is a certain threshold below which we are fine. Even a 20-year-old or a 25-year-old has some, quite a bit actually, of damage in their body, but you wouldn't know it. So, this means that if we take someone who is, let's say, 60 or 70, and they've got plenty of damage in their body, and they are getting sick, or they're about to start declining in health, and we fix even only half of the damage that they have in their bodies, then they will be back to the same amount of damage as they were when they were, let's say, 30 or 40. And that is fine. They will be restored to absolute function, both mental and physical. Of course, we need to do both. So, supposing we try to develop therapies that repair damage, and suppose we become fairly good at it, so that we can indeed repair half of the damage. Let's, partition the damage into two categories, two buckets. We call them easy damage and difficult damage. The easy damage is, by definition, the stuff that we can repair with the first generation damage repair therapies that are perhaps not very far off now. And the difficult damage is the stuff that we can't. Then we can restore somebody from the age of, let's say, 70 to the age of, let's say, 40. Biologically, of course. Now, what's going to happen after that? What's going to happen is they're going to, of course, carry on being alive and damaging themselves more, and eventually they're going to get back to the amount of damage in their bodies that they had before they were treated. Now, here's the tricky part, though. Even if we continue to give them these damage repair therapies every year, every day even, they're still going to get back to the amount of damage that they had before they were first treated, because the difficult damage on its own is going to add up to that amount after a certain amount of time, maybe when they reach the age of 100 or 110, even though there is a negligible amount of easy damage because we're constantly getting rid of it. Here's the critical thing, though. By that time, when they've reached 100, this is 30 years after they were first treated. And we, the scientists, will have been busy during that time. We will have been beavering away, improving the therapy. And that means that when someone is 100, they won't be getting version 1.0 of this damage repair. They will be getting therapies that not only repair the easy damage, but they also repair some, still not all, but some, of the difficult damage. Which means that the 100-year-old will be able to be re-rejuvenated so that they have the damage of a 40-year-old again, or 30-year-old, even though the inherent difficulty of doing so is greater than it was when they were originally 60 or 70. So you get the idea now that in order to keep the level of damage in this person's body down to the level that would naturally exist in a 30 or 40-year-old, all we need to do is progressively improve how comprehensive the damage repair therapy arsenal that we have is. People are getting the state-of-the-art therapy at any point, they can stay one step ahead of the problem. As time goes on and we get closer and closer to being able to repair all the damage, in other words, the damage that's still not repairable gets less and less, it takes longer and longer to become problematic. And therefore, we can even slow down in the rate at which we continue to improve the therapy. So this is why I believe that once we get even the first generation therapies that give us only 20 or 30 years of additional healthy life, we're done. We will never fall below this threshold of minimum rate of improvement that I've called longevity escape velocity. So yeah, sorry that was a long answer, but I felt I needed to go into every step of it in order to get it through to people who may not have heard it before.
No, I love it. I think that's really helpful. And this is what makes your book so interesting and you as sort of a leading personality so useful. is you really give people an understanding of what's happening. And so I actually want to go into these 7 types of damage and the intrinsic nature. That to me is one of the key insights that I got from you is, look, yes, you can slow things down, and you should. I've heard you talk about that before. Absolutely. Eat better. Don't smoke. Exercise. But recognize that, you know, we've been running a 200,000 year experiment, and no one ever has managed to live forever doing just that. So we know that there's going to have to be more. And the way that you look at how that intrinsic damage is done, I found incredibly interesting. So if you can, like, walk us through just like quickly what the 7 types are, and then we'll sort of dip into some key moments in each of them.
All right. So yes, damage repair. So the thing about damage repair that makes it so attractive as a therapeutic modality, a therapeutic concept, is that all we need to do is to identify what the damage is, to characterize the nature of the damage, the differences in molecular and cellular composition between older people and younger people, and then figure out ways to reverse that, to restore that to the young state. Now, let me first of all clarify one thing that people do often get wrong, which is I am not saying that there are only 7 types of damage. There are hundreds and hundreds of types of damage. What I'm saying is that those hundreds and hundreds of types can be classified into 7 categories, and that this classification is a useful thing to do because it corresponds to therapeutic modality. So, for example, one of the categories is loss of cells. So what does loss of cells mean? It means cells dying and not being automatically replaced by the division and differentiation of other cells. Simple idea, right? And of course, this happens in various different tissues. It happens in the brain, it happens in the heart, it happens in the thymus. And in order to fix this, you would need to do different therapies, of course. But all of those therapies come under one heading. They are all stem cell therapies of one sort or another. And stem cell therapies all have a lot in common. Of course, there are differences of detail, sure. But that's really important because it means that if you've got 1 or 2 stem cell therapies working for 1 or 2 tissues, then you've learned a lot about how to get stem cell therapies in general to work. So getting the next one to work and the one after that is going to be far easier and faster than the first one was. This is the general principle that underlies the whole of the approach. We're going to end up with a lot of therapies that we'll be applying to the same people at the same time, but the way we develop those therapies will not be one therapy at a time. Okay, so that's the first category, cell loss. Then there are 2 categories that are all about having too many cells of a bad sort, of a bad type, of one kind or another. One of those categories is cancer. In other words, having cells that are bad as a result of the fact that they divide uncontrollably when they're not supposed to, and they take over. And of course, there are many different ways that people have thought about to address cancer. Cancer immunotherapy has exploded in the past 10 years, which is, of course, much more recently than when I first started thinking about all of this. Back when I first started thinking about this, the only approach that I felt was sufficiently generic for cancer was to address telomere maintenance, the ends of the chromosomes, which get shorter with cell division, and cancers circumvent that typically by turning on a gene called telomerase. So I'm all about trying to stop that from happening. There are various ways to do that. There's actually been some massive progress in that area recently with the development of a drug that essentially turns telomerase into a suicide gene. So basically, when cells are expressing a lot of telomerase and you give the body this drug, those cells just keel over at once, which is much better than the version that I first put forward in 2002.
How do you selectively do that?
Oh, you don't. The point is the selection is done by the cancer cell itself. The cancer cell has turned on telomerase, expressing it at a high level. So cells that are not expressing telomerase are not affected by the drug, but the ones that are expressing telomerase, they incorporate this drug into their DNA, and that causes them to keel over. It's a brilliant idea.
Are the only cells that are expressing telomerase cancer cells? I didn't think that. I thought that many cells.
It's close enough. So the stem cells of rapidly renewing tissues, like the blood and the lining of the guts, they do express telomerase, but only at really trace level, far, far lower than what cancers do. So there's plenty of therapeutic window there, in terms of dose and duration, to be able to kill off the cancers well without having a bad effect, a significant effect on those stem cell population.
And is that universal to cancer? Like all cancer types express telomerase?
Very nearly. Great question. Not quite. About 90% of cancers maintain their telomeres using this method. The other 10% use a method called ALT, which stands for alternative lengthening of telomeres. And ALT is still really very poorly understood, I'm afraid, though actually there's been massive progress over the past few years, and we may be close. But yes, we definitely need to address those cancers as well. And in fact, one of the main weaknesses of my original anti-telomere approach was that if a cancer was expressing a lot of telomerase and you stopped it from doing so, it would switch to ALT. The great thing about this new drug is that the cancer won't have time to do that. The cells die too quickly. The other way in which you can have too many bad cells is if cells are not bad by virtue of dividing too much, but they're just bad in some other way. So they get into a state where they are, perhaps they're still doing what they're supposed to do, or maybe some of what they're supposed to do, but they're also doing bad stuff. And the most well-known category of this, subcategory within this category is cells that are called senescent cells. These are cells that get into a very characteristic state where they secrete nasty chemicals that are bad for the cells around them. In fact, some of those chemicals are oncogenic, so they can actually promote cancer in neighboring cells. But there are other ways in which these cells can be bad. So we'd like to get rid of those cells. Now, again, this is an area where there's been great progress in the last 20 years. Originally, my view was that the only way we were going to get rid of these cells was by essentially a method that's also to do with suicide genes. So essentially introducing an engineered gene with a virus, with gene therapy, into these cells that would cause them to die as a result of the other things they were doing already. And that's still a perfectly reasonable approach, and it's being pursued by at least one company in this space. But the remarkable thing that was discovered less than 10 years ago now is that, in fact, we may very well be able to do this just with pharmaceuticals. There may be small molecule drugs that can actually get in and selectively kill off these nasty senescent cells. And there's a bunch of companies, at least half a dozen companies, doing that right now. So that's all good news. All right, so that's three things so far, and there's all to do with cell number. There was having too few cells, and there was two types of having too many cells of a bad type. Now, the other things are all at the molecular level, and two of them are inside cells, two of them are outside. So let's do the inside first. First one of these is mitochondrial mutation. So mitochondria are, of course, the machine within the cell that does the chemistry of breathing. They combine oxygen with nutrients as a way of extracting energy from those nutrients. And mitochondria have their own DNA. They're the only part of the cell that does, outside of the chromosomes in the nucleus. And, that DNA is essential. There are only 13 proteins encoded in it, but those proteins are absolutely required components of the machinery that makes mitochondria do what they do. And sure enough, that DNA gets mutated. In fact, it gets mutated really fast as compared to the DNA in the nucleus, because the mitochondria is a really bad place for DNA to be. It's, basically the process of extracting energy from nutrients with oxygen is a chemically very hairy, elaborate thing that has byproducts. In particular, it has reactive toxic byproducts called free radicals, which damage DNA. This seems to be bad for us, and we'd like to fix it. But unfortunately, fixing it is easier said than done, because it turns out that even though you think we're not very good at gene therapy, like getting new genes into the nuclear DNA, we have no way to do anything in the mitochondrial DNA. The vectors just don't get there. It's just not going to happen. Not for a very long time anyway. We need a radical discovery to make that possible. But we can do something else. What we can do is we can put backup copies of that mitochondrial DNA into the nucleus, into the nuclear DNA with regular gene therapy. Now, you may think, well, that's not going to work, is it? Because, the DNA is in the wrong place, the proteins are going to be in the wrong place. That's right, that's dumb. But actually, it might not be so dumb, because the mitochondrion is a really complicated big machine that is actually composed of not just 13 proteins, but more than 1,000 proteins. All of the others are already encoded in nuclear genes, in our regular chromosome. And the machinery, obviously, therefore exists to get those proteins into the mitochondria after they've been synthesized in the main body of the cell, the cytosol. So the idea here is to hijack, to co-opt that machinery, to essentially modify the DNA of these 13 genes, so that the proteins become substrates for this standard machinery, and those proteins are imported into the mitochondria along with all the other 1,000, and assembled as if they had been synthesized in the mitochondrion already. Now this, even though I've shown you that it's not nearly so implausible as you might have thought initially, nevertheless it's still really hard. And in fact, people thought of this idea back in the 1980s, and by the early 1990s they'd given up. But I said, maybe you gave up a little too easily, and so we started having a go at this. And sure enough, we have made a lot of progress. We are now at a point, we haven't got it working yet, I'm not going to say we have, but we're far, far closer to getting this working than anyone believed would ever be possible. So, we're fairly pleased with ourselves. All right,
and if you're able to get that first part to happen, do you think that cell now will outcompete? That's one thing I've never quite understood about gene therapy or editing DNA is how do you then get that new version to win?
All right, great question. So in this particular case, you're not quite asking the right question, because it turns out that mutant mitochondrial DNA generally already doesn't win among mitochondria in cells that are dividing. Cells that are dividing reasonably often seem to purify away the mutant mitochondria as fast as the mutations arrive. The ones that are problematic are cells that are not dividing, like muscle fibers, for example. Those are cells in which the mitochondria still are dividing, and some of them are being destroyed, of course. And it turns out that the mutant, at least sometimes, some mutants enjoy a selective advantage. They clonally expand and take over the cell. So the problem is to fix that. Now, of course, if we're putting these backup copies in the nucleus, then that whole problem of selection between mitochondria goes away, because they've all got the same genes, because they haven't got the genes at all. The genes are common to all mitochondria in the cell. The other type of damage in the cell, inside the cell, is a much easier one to explain. It's just garbage, waste product. So the cell is doing a million different things all the time. And of course, different cells do somewhat different things, but they all do a lot of things. And those processes create byproducts. Byproducts have to be eliminated. Sometimes that happens by excreting them into the circulation and having the circulation take them away and excrete them out of the kidney or the liver. And sometimes the byproducts are simply destroyed. Now, that sounds great, and it works well for almost all of these byproducts. But turns out that some of these byproducts are created only very rarely, and therefore, if you don't do either of those things, if you just store them up rather than either excreting or destroying them, that's okay. It doesn't kill you until old age. And of course, old age is what we're working on, right? But old age is something that evolution doesn't care about at all. Evolution only cares about the propagation of genetic information. And therefore, once you've had your kids, you're irrelevant to evolution. That's why we don't have genes to keep us healthy late in life. So we have these waste products that accumulate very slowly, but eventually, by old age, they start to matter. And they cause a lot of the things that are bad for us late in life, like atherosclerosis and macular degeneration. So what we want to do to fix this is we want to get the cell to be better at either breaking down or excreting things that it doesn't normally do. And we've adopted both approaches. In the case of macular degeneration, the particular waste product that needs to be eliminated is a kind of derivative of vitamin A that accumulates in cells at the back of the eye in the retina. And we identified enzymes in bacteria, in fact, that are able to break this stuff down. These enzymes do not exist in humans, but they do exist in bacteria. So we figured out that if we could get those enzymes into human cells, then the problem would go away. The material would not accumulate, and people wouldn't go blind. And it works. We got this to go working in cell culture. We were able to spin the idea out as a startup company a few years ago. And with a bit of luck, it'll be in clinical trials in a year or two.
And the enzymes are so specific that they only attack the unwanted detritus, for lack of a better word.
Yeah. I mean, enzymes are usually very specific. So that's not particularly surprising. And this molecule, you don't find this molecule anywhere else. There are no other molecules in the body that look like, that exist for good reasons and that look anything like this molecule. So it's not particularly surprising that the specificity is there.
And what does the enzyme do if it were to sort of get loose, as it were, and encounter other tissue? It just sort of dies?
Nothing. Well, sure. The enzyme, all proteins have a half-life. The enzyme just never finds its substrate and nothing happens. That's right.
And the immune system doesn't attack it or anything like that?
Okay, so of course that's a very important question. The immune system would generally attack such a thing. But because it is in the eye, we have a stroke of luck because there's basically no immune system at all in the eye. So there are various other early onset diseases of the eye that are being addressed with various other types of gene therapy already, involving either actual foreign genes, but more often human genes. But the human gene is still foreign if someone's got a congenital deficiency of that mutation in that gene, right? Because then they're not making the protein. So, yeah. So, and also, of course, there's the viral proteins itself, the capsid or whatever. But, yeah, you can just do gene therapy much more easily in the eye than you can in any other part of the body. All right. Then there's the idea of excretion. So another of our spin-out companies, Underdog Pharmaceuticals, is looking at treating atherosclerosis by that method. Essentially, they've developed a really cool molecule that's able to go in and infiltrate atherosclerotic plaques and cells that are overly laden with oxidized cholesterol, which is the target in this case. And they basically just extract it. They basically kind of solubilize it, if you like, and bring it out into the circulation so that it gets excreted through the kidney. And of course, that's just as good as breaking it down, right? It means it's gone. So yeah, this is a really cool way to address this problem. We want to do other things that we want to break down in cells, maybe more difficult. We're just starting a project that breaks down proteins that accumulate in the brain. There are various cases of this. So one of the most famous is what are called neurofibrillary tangles in Alzheimer's disease. These are made of mostly of a protein called tau, which gets misfolded and modified. And we've identified a way using a clever type of antibody that can break this stuff down, at least in principle. But as I said, this is a very early stage of the project right now. Okay, so I mentioned that I've done 5 of my 7 so far, and I mentioned that the other 2 are outside the cell, in the spaces between cells. So what are they? Well, the first one is actually just like the one I just talked about. It's just waste product. And again, we've got a case in the brain in Alzheimer's disease. These are called senile plaques. They're mostly made of a protein called amyloid beta. And there's still a question about exactly which kinds of amyloid beta are bad for you, whether it's the big aggregates that you see through the microscope, or whether it's the kind of just a few of these things coming together in what are called oligomers that have damaging effect on, for example, the permeability of cell membranes. But either way, these are misfolded and we want to get rid of them. And turns out that getting rid of stuff like this outside the cell is a lot easier than getting rid of stuff inside the cell. Why is it easier? The reason it's easier is because the machinery that we naturally have inside the cell for breaking things down is really, really heavy duty. But outside the cell, the machinery for breaking things down is far more primitive. So lots of things accumulate there, which would not accumulate if only they were inside the cell. They would be toast. So all we have to do is get them inside the cell. And it turns out that we can do that with the immune system, with vaccination. We can essentially trick the body into thinking that the material is foreign and engulf it like it would a bacterium, and that takes it inside the cell, and then it's toast. So that works now. People have been able to get it working really well in Alzheimer's disease. There are variations on that theme, but one way or another, vaccination against amyloid has been shown to really get rid of amyloid. It doesn't have much
impact. It's being used now?
Kind of. So it's been through clinical trials all the way through phase 3. Unfortunately, if you want to get something approved for medical use, it has to actually have a medical benefit rather than just a benefit that somebody can see down the microscope. And it doesn't, or at least not to speak of. Getting rid of amyloid in the brain, the people do not get better, or at least not much. So you have to ask why. Of course, the one answer could be, amyloid doesn't matter. I think that's a dumb answer. I think that the right answer is that amyloid is not the only thing that matters. And that the other things that we're not fixing with those therapies, like the tangles that I mentioned earlier, the synaptic density and so on, these things also matter a lot. And unless you fix them as well, you're not going to see a benefit. But my bet is still that if you fix all of those other things and you didn't fix amyloid, you'd still also have only a modest benefit. Therefore, it's a fantastic thing that we have this therapy in our back pocket to be combined in the future with therapies that are still being developed.
Man, I'm really interested in what happens as you begin to attack the amyloid. So when, I think about Alzheimer's as sort of a blood sugar disease, diabetes type 3 or diabetes of the brain, and you think of the amyloid as sort of going in and grabbing onto particles that would otherwise be problematic and sort of encapsulating them. If you're taking that out, that seems like it would really prolong the sort of health span, even though you still have the underlying condition or whatever that's kicking off the things that have to be grabbed a hold of. Were you surprised by how little efficacy that has?
Not really, no. A way of looking at it really is that Alzheimer's is aging in microcosm. There are lots of different types of damage accumulating, and there's crosstalk between the processes that create different types of damage, but they're still semi-independent processes. So, it's just like, if you fix 5 of the 7 different types of damage that I'm listing for you at the moment, then again, you will not expect to see all that much benefit. You've got to fix them all. You haven't got to fix any of them perfectly, but you've got to fix them all pretty well.
Incredibly interesting. So as we look into the future, the model sounds really useful, because right now I feel like we're still a long way away from really understanding all of the biology, even just of something like metabolism, which in your book you talk a lot about how a mass amount of the damage that happens at the level of metabolism. But what's our timeline look like? Are we 20 years away from escape velocity? Are we 100 years away?
So we are far enough away that I can't give you a number. In other words, because for any pioneering technology, right? If it's even 5 years away, it's pretty much a toss-up. But I think we've got a 50-50 chance of getting there within 15 years. I think, there's at least a 10% chance that we won't get there for 100 years, but who cares? 50% chance is quite enough to be worth fighting for, right? Now, of course, how we get there, you have to break that down into, what steps need to happen. The big thing that's happened in the past 15 years is basically the acceptance that this is a promising way to go, and the consequent arrival of a lot of money, especially in the past 5 years, from the private sector, which is definitely speeding things up a lot. But there's a long way to go. And so I've already mentioned that there's going to be a period where we take therapies that work individually in small patient populations and combine them. That's bound to throw up a few unanticipated interactions that we have to address one way or another. But even before then, we've got to get all the bits working. Some of them are already working fairly well, at least in some examples. So stem cells for Parkinson's disease, for example, or, as I mentioned already, small molecules addressing senescent cells. And quite a few of the other things are going to be in clinical trials in the next year or two. But they've all got to get there. Mitochondrial mutations, for example, I can see that still being maybe 5 years away from clinical trial.
And so looking at some of the like really promising wins that have got you excited, what are some, like I know there's been some big wins in Parkinson's, or at least certain types of Parkinson's. What are the things that you find most exciting?
Well, remember, I don't work at the level of clinical trial. I'm focused on the early stage stuff. When something is even within a couple of years of getting to the clinic, we've already spun it out into a startup company. So what excites me is typically the breakthroughs that would take me half an hour of background to describe why it's even important, right? But honestly, I'm excited about everything. I think that really the difference between the answer I would give to this question now versus 5 years ago is that 5 years ago, if I was being honest, I would have to have said that there were a couple of strands in which progress was still imperceptible. We were really not making very much headway on mitochondrial mutations. We were also making pretty much no headway on the one that I never got to yet, which is the stiffening of the extracellular matrix, the loss of elasticity. But around 5 years ago, in both of those cases, we cracked it. We made a really important, logjam breaking breakthrough that essentially released the bats, and we started moving much faster on both of those. So now there is nothing where we're really stuck.
Aubrey, your world is so exciting and vast. I mean, it's crazy. I cannot believe that we've already been going for an hour and we've like gotten through chapter 1 of your book. It's really breathtaking, man. Where can people connect with you to learn more about what you're doing?
Well, of course, the right place to go is our website, SENS.org. S for September, E for Elephant, N for November, S for September.org.
Amazing, man. Well, this conversation has been so much fun. I actually, at one point, thought I may have misremembered what time we started because it went so fast. Your book is phenomenal. All the talks that you've given are wonderful. Guys, I highly encourage you to engage with him. Man, you talk about hitting escape velocity and where this is going, and somebody whose voice, the more that we can get it out there, I think the faster things will progress. So thank you, Aubrey, for being here. And speaking of preemptive thanks, if you haven't already, I'll thank you now for subscribing. And until next time, my friends, be legendary. Take care. Thank you guys so much for watching and being a part of this community. If you haven't already, be sure to subscribe. You're going to get weekly videos on building a growth mindset, cultivating grit, and unlocking your full potential.